All right, hello Precalculus friends. I had a request to go through a couple of the problems that we looked at last week because it was difficult to hear either in class or just we wanted to see them again. So I'm going to go through numbers 4 and 5 off of that first practice that we did, or the worksheet that we had a number of problems with from last Monday, last Tuesday, last Wednesday, last Thursday, last Friday, whatever day we met. I'm going to go through numbers 4 and 5. Number 4 here you can see is that Norman window. I'm going to walk you through my thought process and then type things up as we go along. So here we've got a Norman window has the shape of a rectangle surmounted by a semicircle. So we've got a rectangle going around with a half circle on top. All right, the diameter of the semicircle is equal to the width of the rectangle, so that tells us this is the width of the rectangle, but it's also the diameter of the semicircle. The perimeter of the window is 20 feet. Okay, perimeter is the distance all the way around, so that will be that width plus that length plus half of a circumference, or that portion of the semicircle plus that length. Coming back to that, what dimensions will admit the most light? So we're trying to find the greatest area. We're going to find area. So what I think about is area. Well, we have a rectangle and a half circle. So we need to know the area of a rectangle, area of a half circle. I'm going to start off with what I call a verbal model. Think about what makes sense. We want area. Well, that's the area of the rectangle and plus the area of the semicircle. So we've got what I'm calling a verbal model, just words. What does it mean that we're looking at? I'm going to take this, put this into math type, math speak now. So area A. Okay, well we need a formula, something that gives us area of a rectangle. Well, that's length times width. Okay, plus, and the area of a semicircle. Well, area of a circle is pi r squared. So this would be 1/2 pi r squared would be the area of the semicircle. So r is that distance from the center of the circle to the edge. Length, I'm going to go from the sides of the rectangle, and the width is going to be that base, because it did tell us that the diameter of the semicircle is equal to the width of the rectangle. So diameter of the semicircle is across the bottom where it sits atop the rectangle. So that would be our width, that would be our width. I'm just going to say length, and length are the sides there. Okay, so no, come on. The problem with this is we have L, W, R, 3 different variables for our area function. We need it in terms of one variable, so then we can graph this. Now we were told that the diameter of the circle is equal to the width, but the diameter is twice the radius, so 2r actually equals w. All right, that will allow us to make a substitution in our area formula. So I'm going to copy that, paste it. Because we know the diameter of the semicircle, or 2 times the radius, is equal to the width, we can substitute that out. So instead of w in the area formula, I'm going to replace that with 2r. We've taken our area function. We had one variable r. We had a second variable w. We had a third variable l. We have now changed that to be, well, we've got the r and the r. Yeah, we're down to 2 variables, so we're moving in the right direction. Last thing, I want to get rid of that l and have everything in terms of r. So we have the area just in terms of one variable. So I need something that links together with l. Well, going back to the statement, we know the perimeter of the window is 20 feet. That is the distance all the way around the outside. So we know the perimeter is 20 feet. That is the width across the bottom, so that would be w, plus the length up the side on the left and the length up the side on the right, so plus 2l, plus the outer portion, half of the circumference of a circle, so that outer arc length on our semicircle. Now we know that the circumference of a circle is 2 pi r, so the arc length of a semicircle would be half of 2 pi r. So that would just be pi r. So that perimeter statement, W across the bottom, L and L going up the sides, and pi r would be that arc length going on the outside of our semicircle. Well, there's an L. There's also W. But I'm going to make that substitution from above, that W is equal to 2r. W is equal to 2r. We do have like terms here where we've got 2r plus pi r. However, because of the pi, I'm just going to leave that as is. We're going to solve this for L. So this statement, if I solve it for L, we're going to have L equals 20 minus, what am I doing? 2r minus pi r. All of that divided by 2. So I subtract the 2r, subtract the pi r, divide by 2. I can just take this and now make one final substitution into our area formula. So we had L times 2r plus 1/2 pi r squared. We need to replace that L. So I'm going to substitute out wherever there was an L. I'm going to replace it with that statement. Now this as is, the calculator, Desmos, whatever graphing utility does not care about this as a mess. I'm just going to neaten it up because I like to do those things. So what can I simplify here? I'm just going to copy paste. I notice that here we are dividing by 2. Here we are multiplying by 2. So dividing by 2, multiplying by 2, those will cancel. So I'm going to delete that 2. I'm going to delete that 2. I'm going to get rid of the fraction bar that I have. There we go. Now we can distribute the r in. I'm going to leave that as is. So there is our formula for the area just in terms of one variable, just in terms of the radius of that semicircle. I'm going to take that, I'm going to graph it, put it into Desmos so we can visualize, find the radius that gives us the maximum area. So let's go into Desmos. We have now, I'm going to use function notation, so A of r, the area based upon the variable r, is equal to 20 minus 2r minus pi r times r plus, it was pi over 2r squared. Is that correct? That's correct. All right. So we've got this. I'm going to zoom out a little bit. We have a quadratic. So it gives us that our r value, notice my function notation, the output, the dependent variable, the output, that is the area, and the input, my independent variable, is r in this case. So the radius is 2.6, the area would be 28, I'm just going to round that 28 square feet. So going back, we found the maximum, we're going to have the radius would be 2.8 feet, and the area, the maximum area, that maximum area was 28.005 feet squared. That's the radius, that's the area. We can use that to find the width. We can use that to find the length going around the rectangle based from above. So we know that if the radius was 2.8, that tells us our width was twice that, so our width would be 5.6 feet. And our length was based on this statement up above. So we're going to have 20 minus 2 times 2.8 minus pi times 208. I'll just go out and do that. So we had 20 minus 2 times 2.8 minus pi times 2.8, which was all of that cut in half. Hey, it's 2.8 as well. So the length is 2.8. There. Scroll down, our length was about 2.8 feet. So there we've got number 4. Big ideas. Okay, so we had this image. It's asking for dimensions that admit the most light. Most light would happen when we have the greatest area. So area started off with a verbal model. Verbal using words. Well, area would be the area of the rectangle along with the area of the semicircle. Took that, put it into mathematical symbols, rewrote that. So we had a function for the area in terms of one variable. We graph that, find the maximum. Great. Questions? Watch that again. All right, going on to number 5. So Metro Media Cable is asked to provide customer service to a customer whose house is located 2 miles from the road along which the cable is buried. So that 2 miles is that distance, that vertical distance from the road to the house. The nearest connection box for a cable is located 5 miles down the road. So there's the box over here. We've got 5 miles down the road, 2 miles into the house. Installation cost is $10 per mile along the road. So if we go 0 miles along the road, we'd be doing 0 miles times $10. So we go to at most 5 miles down the road. So we could have 5 times 10, or we could be somewhere in between there. It's $14 per mile off the road. So if we're going off the road with those 2 miles, well, that would be there. Or if we're going diagonal wherever we depart from the road and start going into the house, be $14 per mile off the road. Find the length of the cable along the road that minimizes the total cost. Now, I'm going to start off just like I did the last one. Cost that we have is going to be made up with the on-the-road cost along with the off-the-road cost. So starting off with a verbal model, then I'm going to turn that, okay, how do we get a mathematical model to that? So our cost, I'm just going to say C, well, it's $10 for each mile on the road. Well, it gives us, we are going X miles on the road according to the picture. We are $14 per mile off the road. Well, how many miles off the road are we going? We don't know. I'm just going to give that a Y. When we don't know something in math, we give it a variable. So we've got 10x plus 14y. Problem with this is that we need that cost in terms of only one variable. So we need to rewrite that in terms of, I'm going to replace that y, I'm going to substitute something in terms of x. So here I'm going to go back into my diagram. So we're 2 miles off the road. We're up to 5 miles on the road. Now we're going x miles on the road. That tells us that the portion of the road we are not traveling is 5 minus x, 5 minus x. So that portion right in there, what I'm looking at, and because of the diagram, there's a right triangle in here. There's a right triangle in here. Ooh, I just noticed this house, looks like they've got like a cornfield there. They've also got a swimming pool in the back. Who lives 2 miles off the road? Imagine having to clean that if it snows. That would be awful. That's their field where they go and buy 18 watermelons at a time. Anyways, okay, so we're 2 miles here. We're 5 minus x miles along this section of the road that we're not using, and then we're y miles going off-road here. Well, this makes a right triangle. A right triangle connects the 3 sides with the Pythagorean theorem. So we know that actually y squared, that distance, the hypotenuse that we're traveling off the road, is actually 2 squared plus 5 minus x squared. And 5 minus x, 5 was the entire distance along the road. We've traveled x, that means there is 5 minus x distance that we have not traveled. So I'm going to just rewrite this, solve for y. Y would be the root of 4 plus 5 minus x squared. So there we have an equation that we can then substitute for y. We go back to our cost function was 10x plus 14y. Y is that root 4 plus 5 minus x squared statement. So we can make that substitution with that. I don't need parentheses because the root does the grouping there. So we've got this function for the cost in terms of the distance we travel on the road. Let's look back to the question. Find the length of the cable along the road. That is x. That's what this equation gives us. I'm going to take this, I'm going to graph it. and then look for the lowest point on that curve, that lowest value for x. So back to Desmos. I can do this in a graphing calculator. However, so I'm using my function notation. The cost dependent on x is 10x plus the square root of 4 plus 5 minus x squared. There we go. Okay, so we've got that curve. Uh-oh. Something's missing. Why is that not working? Oh, 14. It's $14. Hey, that makes more sense. So here's a good point. I had a graph that doesn't look right. Something's off. There is, if I keep on zooming out, like there's no lowest point. It doesn't just drop off there. There might be something in there. So something's wrong. I went back, noticed that I omitted that 14. All right, so there's that 14. The graph changes drastically. We've got that. Okay, boo, 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 boo. There, I've got a point. Now, I'm using my function notation, my input, output. My input is x here. That was the distance on the road. So if we travel 2.96 miles on the road, 3 miles on the road, we would end up paying $69.60. That is the lowest point on that curve. Yup, doesn't get any lower than that. So that is our minimum. That's the x. That's the cost dependent upon that distance. So we've gone through, solved it. X was 2.959 miles. Cost came out to be $69.60 when I round it. So there we have it. Okay. Oops. Good luck. See you later.